I will talk about my joint works with Guishan Chen and Su Xin Chen. It's about stability of transonic shocks in supersonic flow around the wedge. So it's an outline of my talk. First, I'll give a brief introduction, and then about the shock toler, where the transonic shock solution is, and then I'd like to talk about its potential stability. So first, let me give a brief introduction. So this is a picture I downloaded from internet, and which shows the oblique shocks. So this is a shock ahead of the nozzle of the flight, and also a shock fronts ahead of the airfoil. So there's a lot of shock fronts here. So here we are interested in the shock fronts attached to the airfoil. So mathematically we can model this problem as a wedge. So it's we can understand as the airfoil as a multi-dimensional wedge, and then there's a supersonic flow comes against the against the wedge, and then it appears a shock front in front of it. So so this is a mathematical problem. So to understand this, we use mathematically we use the Euler equation to describe the motion of the fluid, and here we use the steady Euler equations. In general, if we ignore the viscosity and heat consumption, so no fluid is described by these three equations. So it's conservation of mass, conservation of momentum, and conservation of energy. And these three equations actually indicates this Bernoulli's law holds. So this number, this is total energy plus P over rho is constant along each streamline. So this is steady Euler equations, and this system is very difficult. So we give more simplification. So assume that it's isentropic and irrotational. Then the Euler equations can then reduce to
that
the.
means it's homentropic, not isentropic.
Isentropic.
Homentropic. You're assuming constant entropy everywhere.
Yeah.
Oh yes, yes.
Not isentropic is constant for a particle. Homentropic is constant throughout.
Oh,
Which
okay.
is what you are assuming.
Yeah.
Oh, okay. 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 Thank you very much.
Everywhere.
Okay. So and under these two, under these two assumptions, so the Euler system is reformulated as these potential equations. So this why is the potential of the velocity u, and the density can be expressed as a function of the speed of the speed. So which is this can be obtained from the Bernoulli's law. So so then this potential equations and it's a mixed type equation. So when d phi is less than the critical value, which means that it's a supersonic flow, then it is an elliptic equation. And if it's a supersonic flow, which means that the speed is larger than the sonic speed, then it's a hyperbolic equation. So it's a mixed type equation. And and then we are considering shock fronts. So for shock front, it is a strong discontinuity. So that so of course a shock solution is a weak solution, and across this strong discontinuity, we need so-called Rankine-O'Connell conditions, which hold across this shock front. So and which means that the potential is continuous across the shock front, and this actually means the conservation of mass across the shock front. And also this actually this conditions indicates that the tangential component of the velocity across the shock front is continuous. So and then I'd like to introduce shock polar, so-called shock polar for the solutions described actually we can derive from this Rankine-Gonio conditions. So we assume that on both sides of a shock front, the potential is a linear function, which means that the flow is a uniform flow. So it's a constant velocity. So then we're starting from a 2D case. For 2D case, wedge is in this shape, and we have a uniform supersonic flow, and the shock front is a straight line. So then the flow changes its direction to parallel to the wedge. So if the angle of the wedge is small, and the shock front will attach to the tip of the wedge. So we have this picture. And for 2D case, so then the states a supersonic flow ahead of the shock, and the flow behind the shock front, and also the shock position of the shock should satisfy the Rankine-Gonio conditions, and it can be described geometrically by this loop, which is called shock polar. And for this shock polar, for oral equations is described in Courant and in the books in Courant and Friedrichs supersonic flow and shock waves. And these four potential equations, I found this loop in a paper by Kifitz and Warnick, so in 1990. So then I'd like to briefly explain this shock polar. So all admissible Q here denoted the uniform supersonic flow ahead of a shock front. So it's a supersonic, and this is a sonic circle. And so it's a supersonic, and then all admissible solution for Rankine-Gonio condition equations describe Rankine-Gonio conditions. It forms a loop, form this loop. So which means that only these points can be a shock solution. And since we have a wedge and the flow behind the shock front should parallel to the wedge, so the flow direction should be the tangent of the wedge angle. So you see that if the angle is small, then we have two intersections. We have two intersections, which means that we have two shock solutions. And if this is a weaker shock solution, and it can be usually it will be outside the sonic circle. So this is a supersonic shock solutions, and usually this stronger shock is a supersonic subsonic shock. This point is always inside the sonic circle, so which means that behind the shock front it's a subsonic flow. So this is a transonic shock for briefly of the supersonic subsonic shock. And if the angle is a little larger, and you will see that there will be a critical value, critical angle, which is tangential to this loop. I denote it as star. And then this is a critical angle. If the angle is larger than this critical angle, then there was no intersection of this ray with this loop. So then we don't have the attached shock solution. So this is a critical angle. And then you will find actually this sonic circle, this critical angle is inside the sonic circle, which means that the weak shock solution can also be a transonic shock. So in this case we call this weaker transonic shock, and this is also a stronger transonic shock. So this is for, and also if this solution is outside sonic circle, it's a supersonic as a circle. So it's a little complicated, but actually some three cases. So this is for two-dimensional case, the shock polar determined by the Rankine-Gonio conditions. And then for multi-dimensional case, then it's a little bit complicated. So because we have a third direction parallel to the edge of the wedge. So we have here we have a edge. So in this case, we can also obtain the shock polar just a little bit more more steps. First, the conservation of mass across the shock front. So these equations we can have all admissible points satisfy the conservation of mass across the shock front. Is composed with a surface which is obtained from the 2D shock front and which is rotation with respect to U1 axis. So I call it, we call it a shock balloon. And this is just determined by the one of the Rankine-Gordon conditions. And then we have another Rankine-Gordon conditions which says that the tangential components of the velocity should be continuous across the so the tangential velocity is across the edge of the wedge. So which means that the solution to the Rankine-Gordon conditions should also lies in the plane perpendicular to O1, O2. O1, O2 is the edge of the wedge. So which I draw it in the blue part. So then the intersection of this plane and the shock balloon is the shock polar for which is just the Q, S star, and M. This loop is the solution to the multi-dimensional Rankine-Gordon conditions. So and you can see also that we have a critical angle, and S star is the critical case, and so this is this loop is for multi-dimensional loop, shock polar, and then we are going to decide the solution for a given wedge. So then on the wedge we need the velocity should parallel to the surface of the wedge. So so the velocity should also lies in the plane of the wedge plane. So if this plane have intersections with the shock balloon, so we have it should be also a loop on the shock balloon. This P1, P2 here. So then this is decided by the boundary conditions on the wedge, and then so we see that the solution to the given wedge, the shock solution to the given wedge should be the intersection of this loop and the shock polar. So in case that of course it's possible that we don't have intersections for these two loops. Then in this case we don't have attached shock solutions. So which means that the shock solution should go beyond the edge of the shock. So we have a shock just ahead of, not attached to the wedge. So but it's also possible that we have intersections of these two loops, and then in this case these two intersections in general we will have two intersections. So these two intersections means that we have two shock solutions to our wedge problem, shocks to our wedge problem. So then it is similar to it is also the same as a 2D case. But A is always a transonic shock, and B is the weaker shock is possible to be a supersonic shock, and it is also to be a transonic shock. So so then we have two shock solutions. Then it's a very interesting problem. That it's a natural question that which one is a physical situation. So by Coulomb and Friedrichs, they have a conjecture that to determine which one solution is a real physical intersection, we need taking the boundary conditions at infinity into account. And they suggest that if the pressure at infinity is some below operated limit, so then we have wake shock solutions. And if the pressure is higher, then maybe we need a strong shock solution. So so this conjecture says that these two solutions, both these two solutions are also physical, and it depends on the conditions at the downstream infinity. So, but at that time, there's no theory to support this conjecture. And after almost this conjecture is given in 1948, and to now it's about more than 60 years. So to now there's some theory support this theory to support this conjecture. So so it's actually can be classified two cases. One is for supersonic shocks. There's starting from 1960s, there have been a lot of literature on the stability of supersonic shocks. So this is Gu and Schofer and a lot else. So they have proved that the supersonic shock is stable under the perturbation of the wedge, and also under perturbation of the incoming flow. Of course, they are all stability of in a steady case, and also there's some stability theory for the transonic shock. This is a 2D case, and Xu Xinchen and I have give a stability theorem for transonic shock, and also some others, Kim and also Inflation from Nanjing University. So they also have some papers on these topics, although this is some stability, but it's not satisfied because we are not clear whether the conditions at the infinity is. So at the theory, we don't have the exact conditions. So we have later I and Li Liu and Hairong Yuan investigate the conditions to determine the uniqueness of the transonic shock. So we also have a result there. So of course there should have been some a lot of some literature outside of my knowledge. So this is just some related on the well-posedness of the shock solutions on the shock powder. So here I'd like also continue to talk about the stability of transonic shocks. Since we already have some theory for 2D case, so actually we are interested in multi-dimensional case. So we have assume we have MD wedge, and we also have flow in an empty space. So then our problem is that this if we slightly perturb the wedge, the boundary of wedge, whether we still have wave pattern similar as this one. So this is our stability problem. So then it's very simple. Then this problem can be formulated as a free boundary problem. So phi plus is the potential behind the shock front. So since we don't perturb the flow ahead of the shock front, so it's just phi. It's just a uniform supersonic flow. So it's explicitly solutions. So then we only need to solve the potential behind the shock front, and this is between the shock front and the wedge, and the wedge is slightly perturbed, and the shock front is a free boundary, and so this is a direction. So this actually means that we have a rigidity assumption of the flow. So this is a free boundary problem, and then our result is it is interesting that to compare with the 2D case. So this is our previous stability theory for 2D case, which means that in 2D case for shock solution, transonic shock solutions, so except the critical case. So maybe I just recall the 2D case. So this is a shock polar, and this is a sonic circle. So this is the critical case, and in general we will have this is A and this is B. So for 2D case, in general, we may have this when the angle is not so large. So we may have two transonic shock solutions. So and still less than the critical case. So these two solutions for 2D case, we have as long as it is not this critical case, then both these transonic shock solutions is stable with some small perturbation of the wedge boundary. So which means that we have the basically the wave structure as the wedge is slightly perturbed. But for multi-dimensional case, that we can only have by now we can only prove that only this transonic shock solutions is stable. We still have this basically the wave structure, wave pattern here. But whether this strong transonic shock, this transonic shock also have this stability theorem, up to now we have no idea about that. So this is a difference between 2D case and MD case. So 2D case, both these solutions are stable, but for multi case, by now we only know the weaker one has this stability property, but the stronger one we still have no idea. So why we have this difference? So maybe I just 5 minutes. So briefly introduce that. So the idea to solve the free boundary problem is just first apply the partial Hodel transformation. So to use this transformation to reformulate as a fixed boundary problem, and then we are investigating a stability problem. So we may assume that its first derivative is a constant. It's a small perturbation of a constant. So we may assume that this coefficient is just a perturbation of a constant. So and the idea is just I think it's standard, just linearize the equation and use the nonlinear iteration scheme to and prove that it's contraction mapping. So it's standard. So the fundamental thing is to establish the linearized theory. So and since the flow behind the shock front is a subsonic flow, so in this case, this is a second order elliptic equation. So basically, the model problem we investigate the Laplacian, and this is the boundary conditions on the wedge, and this is boundary condition linearized on the shock front. And I have just directly write out the coefficients. Here is just normal to the shock prone by the not the shock polar, just the shock prone balloon, and this is some coefficients here, and So and this is the domain. So we have this this kind of dihedral angle, domain of dihedral angle. So the difficulty here is that we have a singularity here. It's an edge, and also we have a singularity at infinity. So it's two singularities. So then the difference between 2D case and multi-case that if it's a 2D case, then this singularity, this edge is shrinks to a single point, and if it's a multi-case, it's a straight. If n equals to 3, then it's a straight line, and if n larger than 3, then it's a hyperplane. So, but if n equals 2, it's just a point. So this is the difference between two-dimensional and multi-dimensional case. So then of course we have a singularity at the edge here and also at infinity. So we introduce some weighted Holder norms, and beta here it actually indicates have both controls at near the edge and at infinity.
You say singularity means just corner in the domain. It's not singularity and coefficients.
Coefficients is just Laplacian.
Well, but you do after photograph transform you get Laplacian. Or
not Laplacian. Just some. It's actually elliptic with constant coefficient. But we can with the coordinate transformation we can we change to a Laplacian. Sure. So and this is some oblique derivative problem. So this is a domain here, and we have singularity here. So and the weight here have both control near the edge and also have a control at infinity.
Yeah, I have one more question.
Yeah.
So what is the difference between the case of weak and strong reflection from this point of view?
You mean
between S and B and between S and A? What is the difference?
It doesn't. The difference is for the weights here. Later, I will show you. This is just the Holder norms, and actually the working space is we actually impose two weights. This weight is to describe the regularity near the edge, and this is describe the asymptotic behavior at infinity. So so actually we have actually this is later I just found that Marcia and Plevnevsky, they have established a systematic theorem for this kind of elliptic theory. So in about 1970s and 1980s. So and they have established a theory that from MD case, for multi-dimensional case, then we can establish this unique existence theory of the solution to the boundary value problem, oblique boundary value problem, and there's a strict demands a condition that the weights here should all admissible weights. So beta 0 and beta infinity are weights here. So 1 and alpha just the Holder index. So sigma 0 and sigma infinity is actually important. So all admissible weights should lies in this interval between -1 and this number. This number is determined by the coefficients of the boundary conditions, and the nu1 over nu2 is just the normal components of the u1 and u2 of the normal of the two-Shock Coulomb. So and I remark here just this sigma 0 and sigma infinity is important because du actually relates to the velocity, so it behaves as r of sigma 0. So we need since we need velocity is bounded, so we need sigma 0 to be positive, not negative. And sigma infinity is important. It describes the asymptotic behavior, decay behavior. Also, okay, I always know. So this is the behavior infinity. So this condition actually indicates that this number should be larger than 0. So which means that this should be larger than 0. So in the shock polar, in the figures, we can show that U1, U2 is just the projection of the shock polar on U1, U2 space plane. So and you'll find that U1 over U2 to be positive can be only this part, and for this part it's negative. So for multi-case we can only establish the stability theory for these solutions, but for 2D case, the weight or the minimal weight is a little different. It's not the interval. It just needs to satisfy these conditions. It means that this interval can lies in between the eigenvalues, set real numbers between these real numbers. M is when M is 0, then it's just the interval in for weak case. So then for strong shock, since this is negative, so then for 2D case we can choose M equals to 1. For MD case we cannot choose this number. So but for 2D case we can choose this M equals to 1, and then we can choose this sigma 0 and this sigma infinity, and this way is possible to guarantee the well-posed theory unique existence. And then so we also have the stability for strong shock. And a byproduct is that we will find that this is a number positive than larger than 1. This means that U actually is C2 regularity near the coefficient, near the edge. So it's a very good regularity there. So and I should stop. Let's over here. Thank you very much.
3D case should tend to the 2D case when you let the cross flow get weaker. So when does this instability switch?
Sorry,
if you make it slightly three-dimensional with a small cross flow in the third direction, is that stable or unstable for the strong shock?
So you mean for 3D case? Just
a very small cross flow.
Small cross flow. I'm sorry, I don't get you. What do you mean small cross flow?
You put the bridging in other directions, so almost constant.
Yes, in the flow in the third direction.
I'm not sure, but this is based on the linear theory by Marcia and Pravdensky. So actually I don't know. We don't know whether strong shock will still have stability, but because it's an elliptic problem, so even the tangential component is small. It's still possible that we have something out of control.
The stability should become more and more stable as you let it get weaker and weaker.
Technical linearization doesn't talk about smallness.
Yeah. Maybe there's some other techniques can prove this stability of strong shock, but by now we have no idea about the strong shock.
Speaker again.